All right, let's talk about gain scheduled control. This control method is for controlling nonlinear systems where the control gains are adjusted as a function of system's operating conditions. Basically, we choose control gains using a set of linear models where each linear model corresponds to a different equilibrium point of interest, the equilibrium points that we want to operate the system. And the resulting control gains are then blended with each other through scheduling to generate appropriate control signals for the current operating condition. All right, so basically this nonlinear control technique is a popular one that allows to control the system over desired equilibrium points, capturing system's motion. And in this video, I will go with, both theory along with an example because we really need examples to fully understand Gale scheduled control. So let's start with an example modeling. So we have a pendulum. This is the control signal, torque, Newton's meter, angle, length, mg, g is the gravity, m is the mass. I am going to assume everything unity parameters. So you can, using first principles, actual nonlinear model of this system, of this pendulum, can be given by this. Theta dot dot equals to minus sine theta plus the control signal. You can represent this in state space form. Let's say the first state x1 theta, x2 time derivative of theta, and you can write x1 and x2 as a vector like this. Then the resulting state space representation of this nonlinear system is this. Here, x is the state. Let's put the state here. U is the control, and y is the output of the system, basically this theta angle. So you can linearize this system at different equilibrium points. I only would like to focus, for the sake of this video, natural equilibrium points, mainly u equals to 0. And these equilibrium points are basically downward position when theta is 0 and its time derivative is 0. And this is the stable configuration and downstable configuration. Under ideal conditions, if you leave pendulum like this, it will stay, of course, under ideal conditions. And here, theta is 180 degrees or pi radians, and theta dot is 0. Basically, if you linearize this system on this equilibrium point and on this equilibrium point, you are going to get from this linear model. This is the A matrix, B matrix, C matrix. Delta x in this case is x minus 0 equilibrium point. U is this, and delta y is this. These are 0 coming from the linearization. By the way, if you want me to do a video about state space representations and linearization or equilibrium points, let me know and we can go from there. When you linearize the system and on this second equilibrium point, you have this linear system. In this case, delta x is x minus that equilibrium point, u minus 0, delta u, because u is always 0, and delta y is y minus pi. These are coming from the basics of linearization process of nonlinear systems. All right, so since in this case theta dot is 0 for both cases, in what follows I'm going to refer to this system when theta is 0 and this system when theta is pi, okay? All right, so basically we had this nonlinear system. We can represent or actually approximate this system as a gain scheduled system. And we considered for this pendulum example 2 equilibrium points. And for theta equals to 0 case, A1 is this, theta equals to pi, A2 is this. Note that B and C matrices in this case coming to be the same. And to improve the accuracy of this approximation, you can linearize the system in multiple equilibrium points, because more equilibrium points depending on x and u means better representation of the actual nonlinear system. For example, when we deal with pendulum, you can also linearize it on this equilibrium point by setting u to a non-constant number. So in this case, you are going to have 1, 2, and 3 equilibrium points. If you like, you can linearize the system in these configurations 5, so you can go from there. But from a practical perspective, 3 or 4, what I mean by 4, this, maybe like this, you can add this, 4 or 5, will be sufficient. And if you use, the reason I use 2 equilibrium points is to highlight something practical later in the video. So, okay, to represent this system in the gain scheduling setting, let's define alpha first. And alpha is 0 when theta is 0, and when theta hits pi, alpha is 1. So I am assuming x1 will be operated over 0 to pi. So alpha is a function like this that I draw in here. So basically, let's relate a alpha to a1 and a2 when basically you are operating around this equilibrium point, which corresponds to downward motion. Then alpha is 0. When alpha is 0, this will be 0 and this will be 0, so you can ignore the second term. So basically your alpha, a alpha x becomes a1x. Now, when you are operating this pendulum system around 180 degrees or pi, then alpha is around here. In this case, alpha is 1, this term drops, this is 1, now this, basically x minus pi and 0, this is the equilibrium. We subtract this from x, because don't forget, actual x around here is pi. When you subtract pi basically from pi, you are approaching to the 0 equilibrium of the upward motion. And since in this example B and C matrices are the same, B alpha is basically B, C alpha is simply C that we use. Now, say that idea-wise, we design a control signal U1 to regulate this system when alpha is 0, right? Around this equilibrium point. Now, also say that we design U2 to regulate this system when alpha is pi, second equilibrium. So we are looking at operations over around this equilibrium point. Then we can blend these two controllers, since we have two linear models, like this. So when alpha is 0, then this term becomes 1, this becomes 0. So you are using U1 to control this system around this equilibrium point. Otherwise, you are going to use U2 since this term will drop out. So you are controlling the system around this equilibrium point. And basically this control structure will allow you to control your system from 0 to 180 degrees or pi. And this is how we blend these two controllers, and this is called the gain scheduling parameter. For this example, it is a scalar. It can be two-dimensional, three-dimensional, so on and so forth. And of course, as you increase the dimension, things get more complicated. But I am going to explain the basics. All right, now theoretically, we know that we can represent a nonlinear system or approximate as the gain scheduled version. And here A alpha is m by n, B alpha n by m. You have m inputs and you have p outputs. Now, I would like to talk about gain scheduled control without loss of any generality. I am assuming a control architecture which has feedback part, feed forward part. I refer to this video. You can search for it. It is on the website. So for different types of controllers, you can use an integral controller. You can use it state feedback form, output feedback form, doesn't matter. Here I am assuming X is measurable. I am going to do state feedback to explain, to purely focus on gain scheduling. So the same discussion applies to any other control configuration with minimal changes. So basically, for each, what we need to do, for each equilibrium point, we need to design K1 and K2 as I described in this video. K1 is responsible to make each equilibrium asymptotically stable when there is no command. And the purpose of K2 is command following. And after we design K1 and K2, we are then going to schedule them with alpha. I will do this in the next slide. Before I move forward, I would like to mention one critical thing about stability of the closed loop system. When you insert this control signal to this system, you are going to obtain the closed loop system, right? So when you write the closed loop system, it will be x dot equals to A alpha minus B alpha K1 alpha X plus B alpha K2 alpha C. C is the command to track. For this reason, for stability, this matrix appearing in the closed loop needs to be affine, and this quadratic stability condition for a given positive epsilon needs to hold for a positive definite P. To solve this, we generally use linear matrix inequalities. And again, if you want me to make a video about LMIs, linear matrix inequalities, let me know. For now, I assume you know it. And basically, that's it. So now let me focus on the specific example. So for alpha equals to 0 or theta equals to 0 equilibrium point, I am going to choose my first K1. I am going to call it K1A. I am using LQR. I am giving A1, B, some Q1, some R1. And I am going to obtain my stabilizing K1A. For K2A, I am going to choose it to satisfy this condition. Where this condition comes from, again, it is coming from this video. All right, so for the second equilibrium point, I am going to repeat the same. I am going to use A2 for some Q2, R2, LQR command. I am going to find my stabilizing K1B. I am going to choose for command following K2B like this. My first controller for the first equilibrium point U1 will be this. Feedback, feed-forward architecture. For the second equilibrium point, I am going to use the same structure, but I am going to subtract pi and 0 vector because I would like to operate this system, right? So upside, let's say, pendulum, you are here, you would like to drive it to here. This is the pi equilibrium point. So this point is close to pi 170. So you would like to drive 170 to 180 degrees. So that's why we are subtracting this. Same as the comment, right? So you subtract pi from the comment because if you want to going it up, which is the pi, so it is kind of shifting it to stay on the upper equilibrium point. And as from the previous part of the video, for this example, these are U to implement, which is a combination of U1 and U2 with the scheduling parameter. Now, you can either implement it like this or find this form. To find that form, basically, let's take U1 and U2, put it here. 1 minus alpha multiplied by U1, alpha multiplied by U2. You can arrange the terms to obtain this. This is the K1X structure. And basically, you can arrange the remaining terms to obtain this structure. All right, let's look at an example now. So this is a MATLAB example. I am putting the code here so that you can copy paste and play with it. Total simulation time is 30 seconds. This is the first order Euler method discretization sampling. This is the A1, A2, B, C matrices that we found. Without loss of generality, I am assuming I am basically giving the zero initial condition to the system. I use this Q and R matrices, the same for generating K1A and K1B. Here is the computation of K2A and K2B. This is the simulation environment. This is the command signal that I apply. Initially, I am applying pi for 10 seconds, 180 degrees, then 90 degrees, then 0 degrees to the system. This is the U1, this is the U2, and this is the alpha scheduling parameter, and this is the control signal that we inject to the plant. And here is the actual nonlinear system. Basically, theta dot dot equals to minus sine theta plus u. Of course, it's discretized version. I would strongly recommend do the simulation on the actual nonlinear system rather than its gain scheduled version to better understand the performance of your controller. That's why I am using the actual nonlinear system. And this is for data recording purposes. And this is also plotting purposes, figures. You can stop the video. I am not going to dive into details. All I should mention, I am converting radians to degrees here and here to plot theta x1 and theta dot x2. Here are the results. Basically, if you remember, we choose two equilibrium points. One was corresponding to 180 degrees, this, right? Pendulum was up. And the other one was 0 degrees, pendulum was down. For this reason, the accuracy of command following performance is pretty good for the unstable equilibrium point and the stable equilibrium point. However, if you would like to track somewhere between, as you see, there is a steady state error. And before I mention about the steady state error, here is the second state's response. This is the control signal's response. You can you can address inaccuracy by two ways. Adding more equilibrium points, for example, if you also linearize this pendulum system around 90 degrees by applying some non-constant, non-zero control signal, then you can also make this track perfectly. This is way one, or you can resort to higher control gains, K1 and K2, if you would like to move forward with two equilibrium points. So in the next one, I am decreasing R matrices from 1 to 0.01. So I am using a higher control. Decreasing R in LQR, linear quadratic regulator, basically will have a more aggressive control signal, higher gain. So if you look at this plot, I track 180 perfectly as expected, 90 degrees almost perfectly. This dashed line is the command, and black line is the theta, and 0 degrees also perfectly. This is the second state, and this is the control signal. If you realize control signal is more aggressive since we are using higher control gains. So if you would like to avoid aggressive control actions, just linearize your systems also around 90 degrees. Or again, you can, as I mentioned before, you can use 3, 4, or 5 equilibrium points to increase the approximation, gain scheduled approximation of the actual nonlinear system to obtain better control performance without resorting to high gains. All right, that's it. So please, if you have any comments, let me know, typed up. And if you want me to cover any new stuff, also please let me know.